afternoon. I'm doing a project on two peat cores that were extracted from the Carnival region, and I'm using them to explain I'm using pollen analysis as a proxy indicator to reconstruct the palaeoenvironment of the two source sites in the from the source wetlands to the Okavango Delta in Angola. Okay, so what is palynology? Palynology, it's essentially the study of organic microfossils such as pollen and spores, which will be dealt with in my particular thesis. And they're very small, so they require a microscope to study. They're considered palynomorphs because they fall under the region of the study, and they include other species such as diatoms, invertebrates, and marine fossils, which Marion Bamford will talk about tomorrow. They're often found in sedimentary rock, peat bogs, and wetlands. There are various applications to palynology, most concerned with the environment, and fossil pollen can be used to reconstruct paleovegetation, paleoecosystems, paleoclimate, and essentially track climate change. Palynology can help to reconstruct data as far back as 300 million years ago, so going right back down to the Permian. And while in this particular study looking at late Quaternary, you can use the pollen analysis to reconstruct vegetation and track the climate change and how the ecosystems responded to that climate change, as well as determine whether there were any major anthropogenic influences from settlements and fires and agriculture. Palynology is very useful because each plant has a very specific environment that it thrives in, as well as fast evolutionary rates. So once you look at pollen species, you know exactly what type of environment you're looking at when you go back in time. In pollen analysis, you look at the shapes, openings, and ornamentation, so just the morphological features of these grains. And pollen it's only the remains of seed-bearing plants. The reason pollen is so useful and preserved so well is because it contains an outer layer of sporopollenin, which is one of the most inert organic substances. There are certain limitations, such as preservation conditions, so high alkaline environments and high temperatures don't preserve the pollen too well, as well as dispersal, because certain pollen is wind pollinated and some are insect pollinated, certain plants. So obviously wind pollinated plants produce more pollen that gets preserved. There's also an issue of identification, which shouldn't be an issue though, but this won't be a problem for this project because wetlands and lakes produce some of the most well-preserved pollen. The cores were extracted by GOTS from two source wetlands in Crater and Carnival, and further. Sorry.
Excuse me, nobody can hear you back there. Can you move closer to the mic?
Sorry. Okay.
We want to hear what you're saying.
Okay. There were two cores extracted from two wetland sites. Okay. Further extraction of cores from surrounding regions will give you a broader paleo-environmental reconstruction of the whole region, and then to see if there was a Western influence in the area. The aims of my project was to determine the palynology of two major source wetlands to the Okavango Delta, and then reconstruct the paleoclimates and paleoenvironment, and from that look at any major vegetational changes through the years, and see how they've reacted to climate change, or if climate change had any impact on them. This was done by initially extracting the pollen from the samples. The cores were subsampled at a 2 centimeter resolution so that you can provide a high resolution analysis, because essentially the cores are 3,000 years old. So essentially 3,000 years isn't that old, and the higher resolution, the better. So you can look what happened through time. And then microscope work to identify the genus and species. AMS radiocarbon dating, so a few samples were sent to Beta Analytics to obtain the date of the core, which is 3,000 years, ranges from 3,000 years to present. And then the final step, which was reconstructing the past vegetation and climate. The main focus and hypothesis of the study was that the pollen analysis from these two regions will aid in reconstructing what happened in the past. The main steps were fieldwork, chemical preparation, microscope analysis, and statistical analysis. So samples were collected by GOTS because I wasn't able to go to Angola, and they were done using a Russian corer, which is better than a vibrocorer because a Russian corer uses a split sample, so it allows you to get a maximum core without compressing the sample, so you don't get pollen over the years that's been laid down in the sediments getting mixed up. And then once you subsample the core, you undergo various chemical processes to remove any organic matter or any other unwanted plant material, so that you just extract the pollen grains so you can look at them through the slide. Once that was done and the slides are made, I've then done a microscope analysis using a light microscope and identify the pollen grains down to a genus level and not species, because with a light microscope you can't. And to identify down to a species level, it would require scanning electron microscope to go into greater detail, which is a possibility for further research. And so 300 grains per slide was done, and a total of 90 slides were counted. I then did the statistical analysis, which produced all sorts of wonderful things. So there was a Bacon modeling to look at a curve of best fit, to look at trends. Any outliers were removed because these would possibly be pollen that is recent and just contaminated the sample. A principal component analysis to identify key trends in our data. A CONUS, which still has to be done to determine the stratigraphic zones and how they are separated. And then a C2 stratigraphic pollen diagram, which is here. So this is for the Okavango core, and as you can see, here there's a spike in the Poaceae, which is grasses, Asteraceae, which is daisies, and then a decrease in Cyperaceae, which is sedges. So Cyperaceae indicates a wetter environment, whereas Asteraceae indicates drying conditions. So we're going to look at these trends and see what's going on and determine what happened over time, and if any of these were due to anthropogenic influences. This is a pollen diagram for the CS core, and here you can see Poaceae is the most abundant, which is common of wetland environments. So going back 3,000 years ago, you still had that wetland environment. And then to end off, here's some of the pictures of pollen that I've taken using the light microscope. This is an Asteraceae. Both of them are Asteraceaes, and they're both different species. So there is a variety of species within the samples that we've seen so far. So what further research we can differentiate the different species and get a more detailed project. This is a Cyperaceae, which is sedges, and this is a Poaceae pollen grain, which was the most abundant in all the samples, so the grasses. There were a lot of spores in our samples, but they weren't identified down to genus or anything. They were just classified under spores because there's too many different genuses of them, and that's next to a Lycopodiaceae grain. Thank you.